Hello, everyone. Thank you very much for joining Particle Metrics talk about improvements and latest news on fluorescence nanoparticle tracking analysis. I hope you have been well, and it's great that technology brings us together so we can really have a great meeting. I hope all of you are well, and let's start with the talk. I will give you a little overview about the latest things we have been doing with NTA. But let's stop a bit for some basic notions so we have everyone on board. So that's a typical video with nanoparticles, which are very busy in water. So you see the Brownian motion. So that's the heart of nanoparticle tracking analysis. So you capture the Brownian motion and you numerize that. So this was actually the birth of a nanoparticle tracking analysis, size and concentration measurements, particle metrics. From a historical point of view, we come from a zeta potential measuring the surface charge of particles, and 3 years ago we introduced fluorescence as well to have the fluorescence detection capability, and also we look into the subpopulations more from a physical point of view, so how the particles appear on the screen. And all this in detail. If you are more interested about the details, how the technology works, I recommend you our tech note about nanoparticle tracking analysis, which is available in the download section of our homepage. So I will go ahead and talk about applications, what you can do, and where we are with NTA and the detection, the characterization of extracellular vesicles with NTA. So that's a typical image you see here. So that's all particles moving around. The thing is, it's a physical measurement technique. It's not specific. So scatter from a typical scatter image, it's not specific. So you might be wondering, is it your real analyte? Is it a protein aggregate? Or is it your extracellular vesicle you're actually looking for? So that's why we actually need specification. And so that's one major thing I'm going to talk about. So one thing was I just mentioned, you get the overall concentration of your sample. So you know all of the particles which are in there. Contamination included, of course. So, but this is also a quality parameter for your sample. So NTA measures total concentration, and you need this total concentration in order to estimate purity. So this you do by means of a chemical sensor. This is a fluorescent dye, which specifically stains your sample. It can be a membrane dye, which is of course not so specific, but also an antibody. And by having both the scatter information and the fluorescence information, you have a measure of purity, which is a strong asset when you do characterization of your particles. In the same way, if you have several lasers, then the NTA can feature biomarker ratios. So you have different fluorescence channels, different lasers. So this gives you really biomarker ratios, which is very strong. And we have up to 4 lasers, so there's a lot of ratios. Again, we have technical notes explaining how we do the staining, how we do the measurement. Make sure you get one of those as well. Giving you a little bit of history about the ZW family. So we started in 2008 with the first instrument, and then 2010 we developed the PMX 100, and then a few years later, then we improved the cell handling, and so it was much more easier to perform measurements and much faster with reduced sample volume. So this was in 2013, and then in 2018 we combined a second laser. So for the first time, as a user, you were able to perform fluorescence measurements with 2 different lasers on the same sample, saving time and saving precious sample. So we introduced the automated filter, so you do not have to change the filters manually. And we thought we are not stopping there. 2 and 2 is a nice number. So we introduced in 2019, we introduced the quad system featuring 4 different lasers, and you can select from the wavelength of choice. So all of this is the CDV family, and also make sure you stop by our virtual booth so we can present you the instruments, how they work, and what you can do with them. The quad system features 4 different lasers, meaning you have 4 readout for fluorescence, plus you have the scatter. So there's actually 5 channels. So this gives you a lot of stainings you can do, and a lot of applications you can do with it. Of course, we are not stopping there. And in German, we say, vor dem Spiel ist nach dem Spiel, meaning after the ISIF is before the ISIF. So be sure you are in touch with us to get the latest information how we thrive NTA technology. This is a selection of several fluorophores you can use for NTA, which you need for the 4 different channels, ranging from 4 or 5 nanometers up to 640 nanometer, which work on the instruments. So basically, you need those dyes that are directly coupled to an antibody, and the antibody is conjugated to the EVs, which gives you the fluorescent readout. Shifting gears a little bit, going into multidimensional data and what you can do with that. So by multidimensional data, what I mean is actually the physical properties. So you can get out the physical properties of an image, meaning brightness, of course, the number, how much particles are on the screen. So that's a number, an estimate for the concentration. But you can make use of the intensity, so how bright a particle appears on the camera. And this is, of course, linked to the fluorophore per bead. And this is actually, in the long run, what we're going to do. So those the table you see here features several polystyrene, fluorescently labeled polystyrene, ranging from 40, 100, and 200 nanometers. And the fluorophores per beads are given by the manufacturer. So the range is rather huge. So it ranges from 350 to 110,000 fluorophores per bead. And if you're coming from flow cytometry, so the log of the fluorophores per bead actually are more, you're maybe perhaps more acquainted with. So, and this is actually how such particles appear on this NTA screen. So the 40 nanometer are rather dim, the 100 nanometer, you see them nicely, and the 200 nanometers are very bright. So it would be nice, of course, here to correlate the number of beads with a so-called NTA intensity. So you have different populations, and you can see different numbers of fluorophores per beads. So this is where we are at the moment. So this is a heat map, and the color actually represents concentration. And yeah, also you have to keep in mind, NTA technology sees the 40 nanometer fluorescent particles, and this corresponds to 350 fluorophores per bead. This is towards the determination, and I would like to speak about the term ABEF, which means the antibody per EV. So this is the analog to the ABC, the antibody per cell. All right, so I'm also launching today the Multifilter option, or the Multifilter feature, meaning with one laser you can operate now several filters, and this makes sense if you have different Stokes shifts, so different emission properties of your dyes. In the application I picked out here, we excite with a 488 nanometer laser, and then we can excite Alexa fluor dye as well as the PE dye. And if you have the correct filters, you can distinguish between those two emissions. So we did a staining of HCT 116 EVs, featuring a single staining either of the CD63 or the CD81, or a combined staining where both antibodies are conjugated. And first, the principle, so you have the notch filter, which is a high efficient filter to block, of course, the laser light, the scatter light, as well as the emission of the PE. So it's quite a short bandwidth. And if you switch between the filters, you have now a cutoff filter, 550 nanometer, which gets only the signal from the PE. Of course, the Alexa is also also spilling a bit into it, so and this has to be corrected, of course. And this is the result, what we are getting if we do the single stains with the CD81. Of course, in the Alexa channel, you get the signal that's the signal from the conjugation, and you should, of course, not get anything in the PE channel. Of course, there's always a little bit of background, but this is not a big background, so this works rather nicely. The same thing in the CD63, you have the reverse situation. and you have both of them, you have quite nice signal, and this is in quite good correlation with the single staining. As I mentioned, the CD63 signal is larger, and this is because the Alexa fluor is also adding some signal, and this has, of course, it has to be corrected. And then it really represents very nicely the single stainings. So this is the resulting size distribution. Again, this is a single laser instrument, and we did a double determination of antibodies. The gray curve is the scatter curve, keep in mind. So that's the total particles, so the total particle concentration. And not all of them are EVs, but that's the size distribution and scatter of your sample. And then in the other colors, you have the CD81 and CD63. And the peaks are significantly different from the peak. So this is the smaller size, EV smaller than 100 nanometers. So this gives more or less the evidence that we're really detecting EVs and not large aggregates, for example. So this works nicely. If this was a little bit too fast for you, we combined all this information, we collected this information on our e-poster, so you make sure you get your own copy. And just in a nutshell, so we can do fast switching between the fluorescence channels. We are using high efficiency filters. You can use the standard filter, or if you have customized filters, this is possible as well. And a nice asset to have. So all instruments actually are supported. So this can be upgraded anytime on your existing instrument. The next chapter, I would like to share some information about evaluation of the staining procedure. So meaning what is actually the error and about design of experiments. So we did an internal lab study, and this is a typical situation what you get when you have a new student in your lab. So perhaps the data shows a trend or is scattering. Then after retraining, so it's much better. And in comparison, that's user beats and experienced users. So the standard deviation, the precision is really there. And this is a nice thing. So it's not that. So CW can really help in the evaluation of such a pipetting scheme. That's the box plot of user A and retrained user A and the experienced user. So there were 3 technical replicates, and each of the replicate we diluted 3 times. And if you do this, you can aim a standard deviation in the range of 4 to 7%. Again, the design of the experiment determines the precision. So it's both. It's the uncertainty of the instrument and the uncertainty or the sources of errors in the process of sample preparation. Also talking a bit about optimization, and this is now the real staining with the no-wash strategy, meaning we have free dye there, and by the last step from incubation to NTA dilution, we dilute away the free dye so it doesn't disturb. And if you do it in a proper way, we actually can measure without any disturbance from the dye. And this is done by the optimization of the dilutions. In this case, this was the membrane dye, and the measurement takes place at around 50 nanogram per milliliter, but the incubation can, of course, take place at a much higher level. So this is how it actually looks like. So you do variations of concentrations of your dye, and by measuring the background, you have a certain limit where you can measure very nicely. And once you know the dilution, the optimum dilution of the dye, you can optimize your incubation protocol and your protocol about the dilutions. Again, there's also a technical available describing how this works, so make sure you also download this from our webpage. This is how the variation of concentration actually works. So this is done with the antibody, and on the x-axis we have the concentrations of the antibody in microgram per milliliter, and you see that it's actually rising. So there was at a certain incubation time of 3 hours, but if you do a dilution, so if you the orange arrow, the orange bars represent a higher dilution. So for 3 microgram per milliliter, so this is the same. And for the last one, for the highest concentration, you can see the effect already from a little bit too much of free dye, and by increasing the dilution, we are getting back to the staining, so the pure staining, and not picking up the background. So once you do that, you can just increase the dilution, and so by that you make sure that you are not affected by the background. So this is nice. So we have a stable kind. We found the optimum. So the ion of stability, we would say. So it's a 3 microgram plus minus 1, which is quite nice. So you have a range. So in essence, so this was estimated to be a ratio of 50,000 antibodies per EV if we assume a molecular mass of 25 kilodaltons. On the right-hand side, we have the incubation time, and we did monitor the fluorescence signal of 3 individual stainings for over 3 hours, and this is quite reproducible. So once you have the ratio figured out, if you have the background figured out, then this is really nice and reproducible and gives nice, precise results. As an alternative to a single antibody staining, more an alternative or another EV-specific marker, I would say, we tested whether we can use an antibody cocktail, CD9, CD63, CD81, putting all that with the same fluorophore in there and do the staining. Of course, you get a nice signal, which is a sum parameter if you so want, but this gives a quite good signal, and also this is quite nice and stable if you want, for example, a measure which is close to being a total EV count. So we did this for also on HCT 116 EVs on lyophilized, so we reconstituted them and measured them. And so even if there are several days old, up to 21 days old, so the count is the same, which is good news. Last, I would also share with you the information that we launched as security software, which is GMP compliant and also CFR 21 Part 11 compliant. And the new software version features user administration. You have a unique login, which is password protected. We have a database management, so you can load and reanalyze data. Each of the records will be stored in the database. And last but not least, the audit trail, which you can follow up what has been done to the sample and to the analysis. And of course, no record can be deleted. So this is one of the requirements. Yeah, I'll be happy to share this information with you. And this is the end of my talk. Thank you so much for your time and staying with me. Make sure you meet the CW family. We have live instrument showcasing at the Particle Metrics virtual booth. So make sure you stop by, and so we can show you about the latest news on our instruments. Thanks a lot. Please keep safe, and we hope that we can see each other very soon. Thank you very much.